Very good morning to everyone. In this lecture, EC 8351 Electronic Circuits 1, Department of Electronics and Communication Engineering, third semester. Today we are going to discuss about the topic voltage divider bias circuit of JFET configurations. In previous session, we have discussed the self bias and fixed bias configuration of JFET configuration of transistor models. In this voltage divider bias, we have to see the potential divider bias circuit of N-channel JFET circuit diagram. Here the resistance of gate resistance 1 and gate resistance 2 from a potential divider across the drain supply VDD. The voltage V2 across the gate resistance 2, it provide the necessary bit, that is a biasing. The additional gate resistance from gate resistance 1 from gate to supply voltage facilities in large adjustment of the DC bias point and permit use of larger value of the source resistance. The coupling capacitance are assumed to be open circuit for DC analysis. That is first one is the gate is reversed. The gate is reverse bias, so the gate current is equal to 0. And what is the gate voltage? So we have to apply the Kirchhoff's voltage law. The gate voltage is nothing but the is equivalent to the V2 is equivalent to the threshold voltage divided by the gate resistance 1 plus gate resistance 2 into the gate resistance 2. Second condition, we apply the Kirchhoff's voltage law to the input circuit. The gate source voltage is equal to Vg minus Vs is equal to Vg minus Id into Rs. Now what is the drain current of output? The drain current is equivalent to the drain source saturation current into the 1 minus gate source voltage minus the pinch off voltage whole square. And also the output voltage of VDS is equal to VDD minus ID into RD plus source resistance. So the operating point of the JFET amplifier using the voltage divider bias is determined by the IDQ is equal to IDSS into 1 minus VGS minus VP whole square. So the VDS is equivalent to the threshold voltage minus the drain current into RD plus RS. So the gate source resistance or gate source voltage is equal to gate voltage minus the drain current into the source resistance. So we have to finalize the analysis of the drain current is equivalent to the drain source saturation current into the 1 minus of gate source voltage divided by pinch off voltage whole square. Now we have to put the parameters, that is the value of the drain source saturation current into the gate source voltage and also the pinch off voltage. We get the drain current in the output side. Now let us move to the equations. We solving the quadrant equation by the formula of minus beta plus or minus root of b square minus 4ab2 divided by 2a. Here we are applying the initial values to the JFET configurations. If we calculate the value of the drain source voltage, it is taking the drain current in the 6.237 milliamps. Now we have to apply in the VDS and ID. So practically the value of the drain source voltage must be positive. The drain current is equivalent to the 2.417 milliamps. Since we have to calculate the drain source voltage and the gate source voltage and source voltage and drain voltage and drain gate voltage. So now we can applying the formula to the drain source voltage and VDD minus ID into R input resistance RD plus RS and the gate source resistance, that is a value of the drain source voltage minus ID into RS The value of the source voltage is equal to the drain current and source resistance. Now we get the final output of 3.62555 voltage. Now we can move to the another topic, biasing of MOSFET. It is a various biasing of MOSFET configurations. It is one of the UJT family. It is to improve the stability factor of the MOSFET configurations. Here the MOSFET is here two different category, that is a N MOSFET, that is enhancement MOSFET, and a depletion mode MOSFET. Here we have to take the enhancement mode, the N channel enhancement mode MOSFET. Here the circuit is shown in figure. The source terminal at ground potential and is common to both the input and output side of the circuit. The coupling capacitance act as a open circuit to DC, but it allows the signal voltage to be coupled at the gate of the MOSFET. So here the MOSFET is a three different terminals, that is a gate, drain, source. So here we are taking the voltage divider biasing mode of the MOSFET, that is we have to apply the potential difference between the R1 and R2. So the initial condition of the input side and also the output side, we have to take the analysis of gate source voltage analysis and also the drain source voltage analysis. Now as the gate current is equal to 0, it is the initial condition of the MOSFET. In gate voltage is given, that is a 0 volt, so 0 current. Assume the gate voltage is greater than the threshold voltage. Here the MOSFET is biased in the saturation region. The drain current is the gate voltage is equivalent to the gate source voltage is equal to R2 divided by R1 plus R2 into VDD. It is a voltage difference between the voltage divider potentials. So the drain current is equivalent to the Boltzmann constant in the K of VGS minus VT whole square. Now we are applying the Kirchhoff's voltage law in the drain circuit. We have to, the drain source voltage is equivalent to the VDD minus ID into RD. If the VDS greater than the VDS of saturation is equal to the gate source voltage minus VT, then the MOSFET is biased in saturation region. So the drain source voltage is less than the drain source saturation voltage. Then the MOSFET is biased in the non-saturation region. The drain current is given by ID. So here the session we are discussing the biasing method of JFET configurations. Thank you for watching this video.